So I know that someone else is coming, but well, we'll see. So I will talk today, as I said, not about surfaces, but about apolarity. So, so how many of you were at the lecture last Thursday? There was a talk in the auditorium last Thursday, right? Some of you were there?
About Parsing composition, symmetric.
Well, there was yeah, exactly, yes, this symmetric tensor decomposition, yeah. So this is going to be about that. Anyway, it's called the key word today is apolarity. So this is quite different from these surfaces, but it still is a thing that, and I have this paper that some of you got, one more copy here, on this. And this is an area, this is a problem there where there's some activity more recent than the other one. So apolarities. Let's look at the following problem. I take now a cubic polynomial in two variables. A cubic polynomial in two variables. And I ask, can I write f, or can I find L1 and L2 such that f is equal to L1 squared or L1 cubed plus L2 cubed, where the Li are linear forms. Okay. Can I find L1 and L2 such that f is in there? So I want to think of this geometrically. I want to think of this geometrically. So this is a cubic, in binary cubic. Can I write it as a sum of two cubes? I think of this as something, some geometric thing. So this means I think of the space here of polynomials of degree 3 in two variables, monomials or homogeneous forms of homogeneous polynomials of degree 3 in two variables, modulo scalars as a P3. Right? As a P3, I have four coefficients. Okay? And inside, so in fact now I have f, or the class of f, as a point in this P3. Since this is an element there, the class of f is a point in this space. Okay? And where, well, these guys are also points in the same space. These are also points in the same space. So I have, inside here, I have the collection of L cubed, where L is in x0, x1. Right? So these, among all the polynomials, I have the pure cubes. And this thing here is nothing but a twisted cubic curve. twisted cubic curve, right? It's just taking L to L cubed. That's just a triple embedding. Triple embedding. Okay? So now I have the point and I have this curve in there. So maybe I write it or try to draw the curve. That's this curve. And I have my point somewhere. Okay? So if F already is a pure power, there's no question, right? Then I can write this and I just forget about the other one. But if not, if the point is not on the curve, then it's not a pure power. Right? If it's not on the curve, it's not a pure power. So what is now, how can I now interpret this thing? How can I interpret this thing? Well, this is a linear equivalence. No, I'm sorry, the linear dependency between these three cubic forms. There's a linear dependency between these three. It means that these three, as polynomials or as points in this space, are on the same line. Right? So I take here some point and here. So I'm saying this is my L. L1 and L2. So I'm saying I'm looking for a situation where these three are in the same line. Okay? So this is going from this algebraic expression to the geometric thing. You know, through the point there, I want to find 2 points on the curve such that the 3 points lie on the line. But now this I should now turn around a bit, right? Because my question is, I start with F. I start with the F. And I'm starting here, and I'm just looking for points like that somewhere on the curve. Is there possibly 2 points such that the line through the 2 points pass through F? Right? So how would I measure that? How could I see that? Well, in this case here, you see, I look from this point, right? So therefore, these 2 points that I'm looking for coincide. So if I project the curve from that point, they will come together, right? So actually, I have downstairs in the plane, which is down here, if I project from the point, I get the curve in the plane. And if I'm lucky, that curve in the plane has some double point. Or I could put it differently. I know that this curve upstairs is nice and smooth. So such pairs that I'm looking for correspond precisely to the double points downstairs. I can find two such things if and only if there is a double point downstairs. And now you see the whole thing. If I start with a twisted cubic curve, take a point outside, project the twisted cubic curve down to the plane. Well, there will always be a singularity. There will always be a node. It will be a node if you're at the general point, and exactly one node. Exactly one node. The rational curve in the plane has exactly one singularity. So therefore you get this thing here. If you were kind of unlucky if you're on the tangent line, then you would get the cusp downstairs. Right? If you're on a tangent line, then you get a cusp downstairs. And so it's not of the same. So this explains two things, actually. It says that if I have a cubic form in two variables, well, if the form is already a cube, then I'm on this curve. If I am outside all the tangent lines, then I get a node and I get two things. If I'm on the tangent line, then this doesn't work. Then I need three, actually. Then I actually need three. Because the two comes together. And this is, the case here is typically when I take something like this here. That's the point on the tangent line. Where this point here is x0 cubed. Then this here is of this kind. Okay. So what I'm saying is that this monomial, this thing here, you cannot write this as a sum of two cubes. You need three cubes.
Why is that why is that going from there?
So this here goes to this point, right? I get the ramification at this point. So the tangent direction, the tangent of this curve is collapsed. And that's what you see there. You have no tangent point, tangent direction here. Here, you still have two tangent directions. One for this one and one for this one.
Yes, but my question is why is that polynomial, that cubic form and this cubic form have this kind of interpretation?
Why this one have this interpretation?
Yeah.
Well, if you... so how should I write this? X cubed plus, so if I look at x0 plus xt times x1 and then take the cubed,
yes.
Then you see that you get x0 cubed and then t x0, well 3t maybe, x squared x1 plus 3t squared x0 x1 squared and then t cubed x1 cubed. And you see the linear part is this one. Yeah. The linear part is this one. So of course I really, this is the whole tangent. You know, when t varies, you get the tangent there. Okay? So this, of course, you can do this for in very high generality, yes. But anyway. But this is the first picture, you know, and well, where you see the geometry of this situation. I want to write f as a linear combination like this here. Then it means I look at the variety of all such things. That's my curve. And to get this expression, I need a secant line to the curve to pass through f. And in this setting here, I can actually also find how many. There's exactly one. It's exactly one. Okay. So this is the first trick, and now this is not enough to to explain everything about apolarity, but I will give you one more example to see what's going on, and then I will define apolarity. So the next example is quite similar, but it's now with 3 variables, still a cubic. And now I'm not going to so I take L1, L2 up to LR such that F is the sum 1 through R of Li cubed. That's what I'm looking for. Okay? So what would it mean here? What would it mean if I interpret it in the same way in this case? Well, I would then go here to x2, and but it still is cubic forms, and I would look here for this thing, but this is no longer a P3, it's a bigger space, it's a P9. I have 10 coefficients. This is the P9, right? P9, and inside here, this here inside inside here is then not a twisted cubic curve, but is the Veronese embedding, the third Veronese embedding of P2. No, P2, because I have 3 variables. So it's all the cubes in 3 variables. So this is what I end up with as V here is a surface. So maybe I should call this V3 because it's the third embedding. Just like I had a twisted cubic before, right? So now my drawing here is going to be more complicated because I still have this F, but I have this surface inside 9 space, right? And I'm looking for secants, maybe R secant spaces that pass through F, okay? But here is the trick. This is too complicated for me. Here's now a trick. This is to do with the apolarity. So let me write it here.
So when was the origin of polarity in this?
1850s.
1850s?
Yes, Sylvester.
Sylvester first?
I think so, yeah.
But now this is popular.
It's coming back, I mean, but slowly. Mm-hmm. But in this setting here, you know, yes.
But after 90s, 2000.
Yeah, 20 years. But I mean, it's increasing now, I think, a little bit, yes. Anyway, here's the trick. So if I can write, if F is L1 to the 3 plus L2 to the 3 plus LR to the 3. So if I can write, if I have such an expression, now I will take the partials. I will take the partials on both sides. So therefore di of f, this is the partial with respect to 0, to x0. This is going to be L1 0. No, I'm sorry. Let me put it this way. Plus plus R0, L, R to the third. So this is the differentiation that you know. If I take the partial of a pure power, I get this pure power, which was to the third, I get it to the second, and then I multiply by the partial of the linear form. That's the thing there. And similarly for the two other ones, right? And so that's fine. This is just saying that whatever, this was a cubic, now this is a quadric, and I can write this quadric as a sum of these squares. Squares, right? But the point is, I have three different ones. And I'm sorry, 1, 2. I have three different quadratic polynomials. These are all quadratic polynomials. And they are all written as a linear combination of the same squares. These squares, L1 up to LR squared, these appear, all of them, for the same. Okay? So if F is a sum of these, then all those partials are sums of these guys. So this is a very easy thing to do, but now we're going to see what does this mean geometrically. What does it mean geometrically? Well, so now I'm not looking at this guy, but I'm looking at the three partials. And they are all now in the space of quadratic forms. So now I take a 2 there, right? And then this is not 9, but it's 5. Smaller space, easier to tackle. And so here I get squares now. And this is the ordinary Veronese surface. This is the ordinary Veronese surface, right? In P5. In P5. So I have these three animals, or whatever it's called, you know, in P5. These are three this is the span, these are these three guys here. And they span some plane. Okay? And now I have my Veronese surface here. Okay? And what am I doing? I'm asking, I have to be very careful, right? So maybe I have to go a bit above here just to see what's going on better. The surface here goes all over the place, right? Because now what I want is to find L1 squared, L2 squared, L3 squared, etc. up to LR squared, such that if I take the span of all of those, this span should contain the whole plane. should contain all three. That's exactly what this says here, right? L1 squared, L2 squared up to LR squared. All of these, well, this guy is in this span, this guy is in this span, and this guy is in this span. So they should all be in that span. Right? So I'm looking for some linear space that intersects the Bernoulli variety, Bernoulli surface, and is, well, I think I want this to be spanned by the intersection and contain the three. So let me say that again. As these LIs are on V, the linear span spanned by those should contain this thing here. So the linear span spanned by these. So I'm looking for some linear span. I'm looking for some linear space whose intersection with the Bernoulli surface spans that linear space. That's the first thing. And the second thing, it should contain this plane. So I need to find L in P5 such that the intersection of L with V2 and the span of that is equal to L, and L contains these partials. The three partials. Okay. That's what I'm looking for. So now I can start, because I didn't, and so this intersection here should of course be these L1 to the square up to LR to the square. At least it should contain these. L1 to the square up to LR to the square. So now we can try how can we deal with this? Well, first of all, think about the Bernoulli surface. The Bernoulli surface in P5, and I look at linear spaces that intersects this thing. Well, let's take dimension by dimension. If I take just a line, well, line is not so relevant because a line couldn't contain the plane, right? So I should go to the plane at least. Maybe there is some plane that intersects P5 and contains this, therefore coincides with this. But in P4 and P5, the surface does not intersect the general plane. So there are some planes that intersect the Bernoulli surface, but the general plane, I think of this as a general plane, this is not contained in a plane that doesn't intersect the Bernoulli surface. Yeah. So we have to go one step further. What about P3s? A P3 intersects a general P3 intersects the Bernoulli surface in what? Well, the Bernoulli surface is so these have 2 and 3. So the Bernoulli surface is dimension 2 and is dimension 3 in P5. So they should intersect in finite number of points, and that's the degree of V2. So that's 4 points. Okay. So here is a candidate. This is a possible candidate for us. Right? So if I can find a P3 that contains this plane, if I can find a P3 that contains this plane and intersects the Veronese surface in 4 points that span, then I'm fine. Now, this intersection here, if it is 4 points, does always span. Always spans the P3. So that's not the problem. Also, what this here says is that any P3 will intersect it in 4 points. Right? Any P3 will intersect V2 in at least 4 points. It's either 4 points or maybe some curves or something, but the general one in P3 in 4 points. So when I start with my plane, when I start with these guys here, this plane, this here says that every P3 that contains this plane will intersect the Veronese surface in 4 points. Okay? Every single one. So I can take any one of those and I get R equal to 4. R equal to 4. That works. But I can do it, with this construction I can actually see a little bit more, because as I said, every P3 that contains the plane will intersect in 4 points. Well, that means that, well, how many such P3s do I have? I mean, this is a P3 and a P5 containing a plane. It's altogether a P2. Exactly a P2 of such things. So this is what I call the VSP of F4. This cubic here, the different presentations are all parameterized by a P2. It's a P2. By all the P3s that contain the plane. So, and I think of this now as projection from partials. Because in this situation that I described here, the three the span here is inside the P5. And this is a linear space, maybe I call this LF, coming from F. These are the partials of F as points in P5. So I get all these and they span a linear space in there. Inside the same P5, I have a Veronese surface. I have a Veronese surface. So now what I do is I project the Veronese surface from that linear space. I project it from that linear space. Then I map V2 actually to projection from a plane in P5. That maps you to P2. That's a linear projection of the Veronese surface down to P2. Right? So if this linear space here does not intersect V2, then this is a morphism. And this is the morphism. And what kind of morphism is it? This is a surface, this is a surface. It's a finite morphism. A finite morphism. A finite morphism, the one thing you want to know is what is the degree of this morphism. Of degree 4. So it's a 4 to 1. And the fibers are exactly what I described over there. The fibers are exactly what I described. So this is the way I think about it. I take the projection of the Veronese from the partials. And then I get a 4 to 1 map. Okay, in this case. I can interpret this. And this thing here, this can be interpreted as follows: if the cubic, no, I have to be, yeah. So, right, yes. This can be interpreted as follows: if one of these partials here live on the Veronese surface, that's what I'm saying, I'm trying to avoid here. But if one of them lives on the Veronese surface, then I'm in trouble. But that's exactly the same as saying that the cubic, that one of these, well, I think of this as a linear space of quadratic forms. If one of those forms is of rank 1, if one of them is a square, that's exactly when there is an intersection. So if you start with a cubic form in 3 variables, look at all the partials and ask whether one of them is of rank 1, then you're in business on that. See that? So this is a morphism unless one of the cubes, one of the partials is a square. So this is a reasonable thing to see. Okay, so this, together with the twisted cubic, you see, in the twisted cubic case, I just projected from the polynomial itself. Took the twisted cubic and projected from the polynomial to get a unique secant line. Here, well, I could have done that also from P9, but here I go to take the partials first and project from the space of partials. And then it's easier to see this thing here. If I had done this from P9 to P8, the question would be, what are the P3s in P9 that are mapped through the point that intersect this triple Veronese in 4 points? And that's not so easy to see. But here you can see it very easily, what happens when you do this thing here. And what this example tells you is that this old habit or something we learned in high school to differentiate polynomials is actually useful. At least for this, right? This is useful for this here. And that's exactly what apolarity is about now. That you use this differentiation. So now I will say something more general about that. So now I take F is in S D xn something like this here, very general, like that. And then I have T, which is a copy of this, which I just now, maybe I call them y1, y0 up to yn. But I think of this also as the ring of differentials. So polynomials in differentials, right? Polynomials in differentials. And so I see that T acts on S by saying delta I times xj is equal to delta ij, the Kronecker symbol, right? So I just simply differentiate. So I would also call this yi applied to xj is equal to this here. So now I see the following, that SD is natural dual to TD. Because if I take F in SD and G in TD, then G of F is an element in K. Right? If I start with a polynomial, homogeneous polynomial in D of degree D, I take a partial polynomial, polynomial partials, apply it to F. If the polynomial partials also has degree D, I'm talking about order D differentiation, then I get down to a constant. Every term is a constant. Also this, so G then applied to SD is a linear map. Differentiation is linear in a sense. So therefore these two spaces are natural dual spaces. Natural dual spaces, right? So I can think of T as polynomial ring on or a coordinate ring, I should say coordinate ring, on P of S. So P of S1, S1 is just the linear forms here. S1 is just a linear form, so this is a n space, this is a Pn. And now I think of this here as the y here as a coordinate ring on this. You see how, well, it's a little bit odd the way it works here, because the points here, so if L is a point here, and G is an element in TD, then I evaluate this at the point L by taking the dth power of L. So here G is a, you see, otherwise all of G would kill anything. If G has degree D and D is bigger than 1, it would kill everything, right? So the one thing, but the evaluation at the point, I should say at the point here, that's what I get by just evaluating this guy here. So it depends on how, on that. So this is a little bit of the awkwardness, but it doesn't, it's not a big problem actually, because if we think about the kind of situation that we've been looking at, then you have P of S1 inside P of SD as a D upple embedding, namely taking L to the dth power, right? And I have my F in SD, then F lies in the span. This is the kind of thing I've been looking at. It lies in this span, right? That's what I've been trying to do. If and only if every G that kills all of these guys, G such that G of L1 and all the way up to LR to the D equal to 0 implies that G of F is equal to 0. So let me explain that.
What is G? G?
So G is in TD, TD.
Or? Not or.
So no, I'm saying for every G such that this is the case, G should also kill F.
Yes. But what is equal to only F?
So if this is the case, then this F is in the span of those. F is in the span there if every G that kills all of these also kills F. So this is the kind of duality that we've been seeing, namely G, the TD defines the hyperplanes. This is the dual space to SD, right? So G defines a hyperplane. So now this point is in the span of these. If every hyperplane that contains those also contains this one. If every hyperplane that contains all of those also contains this one. That's exactly what I need, right? And here I see this is a hyperplane that contains all of these. It should also contain this one. That's equivalent. Those two things are equivalent. Okay? So this statement there is the apolarity lemma. So it says that F can be written as a linear combination lambda I L1 Li to the dth power if and only if the ideal of these points is contained in whatever kills these should also kill this guy, is contained in the annihilator of F, which I call also something like this here. And it is exactly the G such that G of F is 0. Okay. So I didn't prove it completely yet. I will prove it completely just in a moment. But let me just explain from there to there. Right? So here I had this nice duality in SD in the space of forms. Now I look at the ideal of this set of points. The ideal of this set of points, that's all the forms that vanish in all these points. All the forms in T that vanish in all these points. Among them you have certainly these G. The G that are 0 here, they certainly are in this ideal. So I take all those and I want all of them to be in the annihilator of F. And the annihilator of F is something even more, it's easy to define, it's not so easy to think about, but it's easy to define. It's all the differential operators that kill F. That's what I asked for there. Okay? So what is it that I didn't prove? Prove. So if G is in TD, then then I'm exactly here. So if I look at forms not in the whole ideal but just in degree D, in the degree D part, then this is exactly what this says here. So of course I just can compare this here degree by degree and see whether this is equivalent, right? If that's so in degree D, this is certainly equivalent to that. So now I just want to see what about the whole ideal, not just in degree D. So in degree D, this is okay. If G is in degree bigger than D, if G here kills all of these and G is in degree bigger than D, then when you move over to this side here, you see if G has degree bigger than F, it will always kill it. So then the statement is actually void, doesn't say anything. Everything in degree bigger than D will kill F. So that is certainly also okay. That doesn't interfere in my thing, right? So now what is there more to do? So I only have to worry about degrees less than d. I always only have to worry about degrees less than d. So then for that I look at the ideal of E, where E is less than D. So I look at these guys that are there. I want them to be there also, right? Okay. Well, if I have such a thing, yeah, so which way should I say? Which way should I write this? Well, if G is in this ideal and G kills all of those guys, then if F is written like this, it will also kill F. So this way it should be okay. So G intersect Li squared, or L to the eth power, equal to 0, implies G of F equal to 0. So this way, so I'm looking at this equivalence. If you write it this way and G kills all of these, then it will certainly also kill F. So I also only have to go the other way. So I'm looking at the G let me see. So for that thing, let me first put it this way here. The ideal I is just the saturation of the ideal in degree D. Okay? So what I should say here is less than or equal to D is just a saturation of that. I look at the ideal here. I look at the ideal there. Then that ideal in degrees up to D, there I just get the whole ideal by just saturating the degree D part. And what does it mean to saturate? To saturate means whenever y0, G up to y n G is, if those are in the ideal ID, then G is an ideal. So that's saturation, right? Whenever all of these are in the ideal, then also the next one should be. Okay? So that's what I can use now, because I know the equivalence in degree D. So everything is okay in degree D, right? So where should I write it? So everything is okay in degree D, and my new ideal here is exactly the saturation. So I know, if I now know that if G is therefore in I, so i.e. G of L1 to the E equal to G LR to the E is equal to 0. That was this part, right? Now y0 G up to y1 yr d and G, these are also in the ideal, but now in degree D. And in degree D, all of them kill F. All of them kill F. I know in degree D that this annihilator is inside there. So all of those kill F. So if I look at that expression now, you see, well, these partials I can switch around, so I get the G of y0 of F and G of y n of F, all are 0. So G of every partial, G of every partial of F is 0. But this is possible only if G is equal to 0. I'm sorry, G of F. Yeah, so maybe I should have, maybe it's really easier to see it right there. Actually, yeah, I'm sorry. I shouldn't have done this. I'm sorry for confusing you. I know that all of these, so I take the G of F, whatever that is, it is some polynomial of degree at least 1. When I take all the partials, y0 up to yn of this polynomial, I get 0. Then G of F must be 0. Okay. Anyway, so this is the apolarity lemma. And so maybe I should explain that briefly here in this setting here, what this apolarity lemma now says. Right? And this projection from partials. Because if I look at a cubic, this F here, this F, then what I'm aiming for here is F orthogonal, the annihilator. I want to see what is the annihilator. So the annihilator of this guy here is in fact well, could it be any linear form? Try to see the ideal. Well, there is no linear form that kills the general cubic, because then it would be a partial that is zero. That doesn't work. That's only the case if the original thing, the cubic, is really a form in 2 variables instead of 3. So if it's not the cone, then this is not the case. So what about quadrics? Quadratic forms in the Y's. Well, here that's exactly what we've seen. We see the partials of f, they span a 3-dimensional subspace of this 6-dimensional vector space. T2 is just that dual space, dual to this one here. T2 is the dual space to this, to S2, which is here. And inside T2, I get all the forms that kill F. Well, they will also kill, in degree 2, they will kill all of these guys. So this is Q1. It's the 3 quadrics in 3 variables that kill F. The 3 quadrics. These 3 quadrics are the ones that kill all the partials. So it's exactly the dual of this one. So this lemma here also says, I mean, what it really says is that if you take all the partials here, or everything that kills all partials will be in the ideal. So these 3 are in the ideal. And it turns out, so that's only the quadratic part. There could be some, a priori there could be some more in the cubic part, but in fact there is nothing in this case. And these 3 quadrics are exactly the ones that define the map of P2 to P2. This projection here is really the one, so if I think of P2 to the vernice and then project it back, this map here is defined by the 3 quadrics. Those 3 quadrics. These are the ones, these quadrics are the hyperplanes that contains this thing here. So I will not go much further, but I will a couple of more things that are crucial in this thing, this here, and that's the issue of Gorenstein. So I mean, this is really Artinian Gorenstein rings. Because notice when I have my F SD, then F orthogonal lives inside TD, well, it's not only there, it lives in the whole T. And I can take the quotient I call this AF. That's the quotient by this ideal. Right? Now I've forgotten about geometry. This is just rings. algebra. I've started with my f, and I look in a dual ring, what are all the polynomials that kill f? That's an ideal. The quotient is a ring. Okay? So first of all, this ring is Artinian. It's a finite dimensional vector space, because every form here of degree more than d will go to 0. They are all in F orthogonal. So if I just look at this guy here, it has entries only up to degree d. Everything else is 0. So this is Artinian. But the beautiful thing is that this is also Gorenstein, and Gorenstein is something. So this here is the sum of a f I, from I is 0 up to d. This is the grading of this ring. This is a graded ring. When f is homogeneous, then this is a graded ring. And hi, which is the dimension of hfi, is symmetric. So hi is equal to hd minus I. In particular, hd is equal to 1. No, only hd. So this here is symmetric like that. So in this case here, I get 1, 3, 3, 1. So this here is the constant, and then here I have y0, y1, y2, and here I have the orthogonal of this one, and then I have a 1 there. So this is a Hilbert function, as I call it, for this f. 1, 3, 3, 1. Here it's this is the quotient. So from t I get a 1 and then a y0, y1 and y2. In degree 2, f orthogonal has 3 elements. So there is 3 left here. And then in degree 3, there's only 1 left, and this comes from the fact that f defines a linear form. So f orthogonal in degree 3 is just a hypersurface. So I get just a 1 there. Right. And this is complete, and there's a pairing and everything, in this. Okay? Now the big result, in a way, this is due to Macaulay, says that every Artinian Gorenstein ring, which is graded, comes from a polynomial. This way. Every Artinian graded Gorenstein ring is of this kind here. And it defines the polynomial uniquely up to scalar. So whenever you see an Artinian Gorenstein ring which is graded, there is a polynomial somewhere. For instance, a cohomology ring, there is a polynomial there, such that the ring is a polynomial defined by the polynomial ring, a quotient of a polynomial ring by the annihilator of one polynomial. So that's this thing. Next one could say what happens then in different dimensions, because there are some general results on Gorenstein rings, Artinian Gorenstein rings, or Gorenstein rings in general. If the number of variables, so if n is equal to 1, then you have two variables here. Then F orthogonal is the complete intersection. When n is equal to 2, there is a Eisenbud-Buchsbaum theorem, which says that the generators of the ideal of F orthogonal are the profunions of a skew-symmetric matrix. So in these two cases, you actually have some very explicit about these things. In particular, this here is such a case, and here you have three quadrics. Those are the profunions of a skew-symmetric matrix. If I take some matrix of this kind, Q1, Q2, and Q3, minus Q1, minus Q2, and minus Q3, with the zeros in the middle, I have the skew-symmetric matrix, and this is the thing. This is, of course, a complete dissection also. So these things show up this way. So the remaining link now back that I will tell you is just one more time the polarity lemma. Namely that so to find a power sum presentation of F is the same as finding an ideal in F orthogonal that defines a set of points in Pn. So what I'm expressing there is the ideal of gamma inside F orthogonal, where gamma is a set of points Pn, I'm sorry. So this is all just expressing it again. This is an algebraic way of expressing what I said earlier geometrically. If I start with a given polynomial, I can look at the orthogonal. This is easy to compute. You just take all the partials and see what are the partials that kill. You get an ideal, and now what you want to find is some smaller ideal some smaller ideal, something contained there that defines a set of points. And what is the tricky, why is this so difficult or something? I mean, this is the key thing one should think of is that F orthogonal as an ideal does not define anything. It defines the empty set in projective space. It defines the empty set in the projective space. So this way you want to find this geometrically. It's kind of saying you have this lambda f and it's contained in gamma. So if ideal of gamma is contained in F orthogonal, then of course you just switch the two around. And so that's what you're looking for. Of course this empty set is not so easy to see, right? It's not so easy to see. So, but you can play with it as ideals, of course. But this is the apolarity lemma in the algebraic setting. This particular ideal, can I find some smaller ideals, nice and smaller ideals, that define sets of points? So let me conclude here by looking at this example one last time. Here is my F orthogonal. It's generated by three quadrics. The three quadrics in the plane defines nothing. This empty set of that F. It's three conic sections. They have no common zeros. But now what I'm asking is to find some ideal inside here that does define some points. What is the minimal R such that I can find such an ideal? What is the minimal R? That's what I'm asking for, right? What is the minimal R? And so I found, in this case here, I found 4 points many ways, right? Can I find it here? Well, I see it right away. I mean, what are the ideals that define 4 points in the plane? Well, that's just the complete intersection of two conics. Two quadrics will define that. So if I just take two of these, they generate an ideal that is contained in this annihilator. And they define 4 points. Those two define 4 points. Those define 4 points. Any two-dimensional subspace in this three-dimensional space of quadrics, of conics, any two-dimensional subspace will generate an ideal of 4 points. And this is the way you get P2 once more. You get all the two-dimensional subspaces in the three-dimensional space. That's the P2. That was the VSP for the quadric, for the cubic. Okay. So the interesting thing is this apolarity where you actually go the wrong way. You don't look for subvarieties in a variety. You go the other way around. You start with something which is, well, in this case basically empty, and you find something slightly bigger, just points containing this empty set. And so in general, more generally, apolarity can be defined by saying whatever is apolar to, so this kind of inverse inclusion, where you build up. Look at, if you have a curve, you can ask, of course, what are the hypersurfaces containing this curve? What's more interesting in this perspective is what are the surfaces containing this curve? If you have a curve in P, big Pn, what are the surfaces containing this curve? That's the kind of apolarities question, And in this paper here that you have, some of you, and you certainly can find on the archive and on my webpage, it's explained in many more cases how you can get these. And The unknown, there's lots of problems, that are not solved in this. And for degree, well, everything in n degree in 2 variables is solved. In 3 variables, when you start with degree 9, it's completely unsolved. We know the dimension, but we don't know the more precise. And another very interesting case is quartics in P3. This is a 5-fold, and it's completely unknown. And so there's some really, There are other kinds of problems also that I could have mentioned, but I think I should stop with this here. Okay? Thank you.